All right, guys, everybody have a graphing calculator and a note sheet.
Yep.
First thing we're looking at is the fundamental theorem of algebra. So the table here shows several polynomial equations and their solutions, including repeated solutions. So if we look at the first equation on the chart, 2x minus 1 equals 0. The degree is 1. The solutions are actually 1/2. If we went and solved it, we would see that the one solution is 1/2, and it has one solution. The next one on the chart, x squared minus 2 equals 0. The degree is 2. The solutions are plus or minus the square root of 2. The number of solutions is 2. Our third one, x cubed minus 8 equals 0. The degree is 3. The solutions are 2 and negative 1 plus or minus I squared of 3. And the number of solutions is 3. And our last one, x cubed plus x squared minus x minus 1 equals 0. Its degree is 3. The solutions are negative 1, 1, and the number of solutions is 3. Now, what we're highlighting is two things. One, if we have a polynomial of degree n where n is greater than 0, then the equation f of x equals 0, this polynomial equation, has at least one solution in the set of complex numbers. Well, all that's saying is, well, we can say that x is equal to 4 is our solution, yeah? So according to this, we have to have at least one in the complex number, or one as a set of a complex number. Well, it's now a complex number. I mean, any number is a complex number. We can just write 0i, which is neither here nor there. Corollary, if f of x is a polynomial function of degree n, where n is greater than 0, then the equation has exactly n solutions. The degree and the number of solutions are going to be the same. So, if we look at this here, so on the back of that first page, x cubed plus 3x squared plus 16x plus 48 equals 0. How many solutions will this equation have? It's going to be 3, because again, according to the fundamental theorem of algebra, the number of solutions is equal to the degree. Now, if we wanted to find out and we went and found those solutions, the solutions would be negative 3, 4i, and negative 4i. So if we actually solved it, we're not solving here. We're just trying to state the number of zeros, number of solutions. It's 3. And we do indeed have 3. 4. Because the degree is 4. Interestingly enough, the solutions are negative 2, negative 2, negative 2, and 0. Even though negative 2 is repeated 3 times, it is still counted 3 times. Because if a solution is repeated, we count it multiple times.
4.
Yeah, 4. Because the degree is 4. 3. 5. Well, here we have to slow down a bit because it doesn't ask us how many zeros, it asks us to what? Find them. So here, we need to find the zeros. We need to find the solutions. Now, the methods that we went over in 3.5, so, all right, guys, focus up here. So the methods we went over in 3.5, the rational zeros, those are getting us ways to try to find these zeros. And one of the ways we can do it is, yes, we can graph this. Now, when we graph it, the number of zeros I want to get, I want to find at least, for this here, is 3 out of the 5. Because if I can find 3 out of the 5, I can take it from a 5th degree polynomial down to a 2nd degree. I can take it down to a quadratic. Completing the square root method, factoring, we have ways to solve a quadratic. So if we can plug this in, there we go, plus x to the third minus 2x squared minus 12x minus 8. If we can plug this in and graph it and find at least 3 solutions, we can get it down to a quadratic and we can solve from there. Were we able to graph this, get this plugged in and graphed? So we can only find 2. We do have -1 and 2. Now, -1, if we look at the graph, it does look like it touches the x-axis but does not cross it. Those, again, are even multiplicity, because if it touches the graph but does not cross it, there's a good chance there's a second 0 there. And we can check and see. But we know for sure that x is equal to -1 and x is equal to 2. So that gives us a good place to start, because we can at least do synthetic division with those and reduce the degree by 1 each time. Numbers across the top, we'd have 1 for x to the 5th, 0 for x to the 4th, 1 for x cubed, -2 for x squared, -12, and -8. We bring down the 1. Do we want to use -1 or 2 first? 2 times 1 is 2. 0 plus 2, 2. 2 times 2 is 4. 1 times 4 is 1 plus 4. Yes, thank you. 1 plus 4. 1 times 4 would be something different. 1 plus 4 is 5. 2 times 5 is -2 plus 10 is 8. 2 times 8 is 16. -12 plus 16. 4. 2 times 4 is 8. 0. Now that's what we should expect to get, because again the calculator told us that when x is 2, the y value is 0. According to the remainder theorem, if we plug the value in, it should give us the same as the remainder when doing synthetic division. So now we can move on to -1. -1 times 1 is -1. 2 plus -1 is 1. -1 times 1 is -1. 5 plus -1 is 4. -1 times 4 is -4. 8 plus -4 is -1 times 4 is -4. And -4 plus 4 is 0. Questions on this here? No. Now again, commented on the fact that at -1, it does look like it touches the x-axis but does not cross it. So there's a chance that -1 works again. -1 times 1 is -1. 1 plus -1 is 0. -1 times 0 is 4 plus 0, 4. -1 times 4 is, and 4 plus -4 is 0. -1 again. So yeah, so up in our number of solutions, we can say -1 works twice. Because if it's going to work twice, it doesn't matter which order we could have done it. We could have done -1 twice to begin with instead of 2, -1 once, -1 twice. It wouldn't have worked both times. Because if it works at one spot, it works at no matter where in the process. But we did get to the point we wanted, because our variable started off at x to the 5th, x to the 4th, x cubed, and where we're at now, it is now at x squared. And if we put the variables back, what we're left with is x squared plus 4 is equal to 0. Questions on how we got to this point here? Now, one thing we could do here is I can grab the graphing calculator, clear that out, and say x squared plus 4, graph it, see where it crosses the x-axis, because wherever it crosses the x-axis is the solutions. Does it cross the x-axis? No, because in August, a few months ago, we would just say no real solutions were done. But we actually have ways to solve this here. It's just that the solutions are not real numbers. Different ways we can go from here. One of them is the quadratic formula. Do we have a middle term? Do we have an x term? No. Instead of doing that, we can use the square root method. Square root method says get x squared by itself. So we can subtract 4 from both sides. Telling me that x squared is equal to -4. Is x squared by itself? Square root. Now between these two here, the square root of x squared is x. Whenever we take square root, we got to put the plus or minus. Yes. Because the negative inside this radical is going to come out as I. It's going to come out as I. It's going to come out as our I. So what that leaves us with finding is the square root of 4, which is 2. So it means our last two solutions are positive, negative 2i. Positive 2i, negative 2i, that's 2. We had 3 to begin with, giving us a total of 5, yes? Do we have all 5 solutions? Yeah. Questions on this here? So really, even if we got stuck, especially on the test, we graphed it, we get 3 out of the 5 solutions. That's most of the problem done. Now, what would have been really nice is if we graphed this and it gave us how many solutions? 5. If it gave us all 5, we're done. It gave us all of them. We don't have to do anything else. But we always want to get it down to at least a degree 2. So if we can get at least 2 less than the degree, we can solve for the last 2. Questions on this here? We ready for the next one? And again, there's different ways to solve it, but the first thing I do is graph it, especially since we have these nice graphing calculators. Y equals x cubed plus 7x squared plus 16x plus 12. Yeah. And again, yes, the degree is 3, so we need how many solutions? 3. Now for this one here, since it's degree 3, we really only need 1. Because if I can find 1 solution, it'll get me down to a quadratic. If I can get 2, that's even better. So we have -2 and -3. Now the one that we do first for synthetic division really doesn't matter. We just need to use one of them. So going across the top, 1, 7, 16, 12. So do you want to use -2 or -3 first? -2. So we'll do this again. -2 times 1 is -2. 7 plus -2 is 5. -2 times 5 is -10. 16 plus -10 is 6. 2 times 6 is -12. And 0. Now at this point here, if we wanted to stop and plug the variables back in and solve the quadratic, we can. Let's go down one, because instead of using the quadratic formula factoring, I already know one of the others. It is -3. -3 times 1 is -3. 5 plus -3 is 2. -3 times 2 is 6 plus -6 is 0. Now at this point here, we can plug the variables back in. Remainder, term without x, term with x. So we're left with what? X plus 2 is equal to 0, yes? Solve. We wouldn't. It does. So the question is, why isn't it shown on the graphing calculator twice? Let's go window, -4 to, not 1, -1. Let's go by 0.3. Yes, let's go from not 0. Go from -1 to 1 by 0.2. So if we look at this one here, so I mess with the scale and we can see that it does touch the graph and goes back up. But with this here, because it's such a quick change from -3 to 2, it's hard to just see it on the calculator. Does that make sense? But luckily for us here, we got enough of them to get it down and solve. Now, if we had stopped here, where it was a quadratic, it would have given us x squared plus 5x plus 6, and then we factor from there. Well, I don't know about y'all, I think y'all would rather solve x plus 2 over x squared plus 5x plus 6. It's a little bit nicer. If we have the zeros, keep using them until we run out, and then solve from there. Questions on this so far? Let's look at the next one. Y equals. I don't know why you're thinking. Okay. There are. That's part of the why I closed that down, because I don't know how long it was going to take for it to do whatever it was trying to do. X to the 5th minus 3x to the 4th plus 5x cubed minus x squared minus 6x plus 4. And I think y'all have already got it graphed, yes? So we see that we have at least 2, probably 3, yes? Because where it touches the graph and crosses, there's a good chance there are 2 there. Interestingly enough, it's not going to work out for this one, but where it crosses at -1, it can actually have 1 or 3. Because when it crosses the x-axis, it's what we have an odd multiplicity. It shows up an odd number of times. And if we look at the table, we see that it's 0 at -1 and 1. One for x to the 5th, -3 for x to the 4th, 5 for x cubed, -1 for x squared, -6 and 1. Now, whichever one we do first really doesn't matter. We can do -1 or 1 first. Which one do y'all want to do first? -1. The only time I have a preference on which one goes first is if 0 is an answer. If 0 is an answer, it's nice to do first, because just multiplying by 0 and adding makes it nice. -1 times 1 is -1. -3 plus -1 is -4. -1 times -4 is 4. 5 plus 4 is 9. -1 times 9 is -9. -1 plus -9 is -10. -1 times -10 is 10. -6 plus 10 is 4. And -1 times 4 is -4, and we add it to get 0. Which one can we do next? Well, the other one we have is 1. 1 times 1. 1. Yeah. Antler's getting in the way. Negative 4 plus 1 is negative 3. 1 times negative 3. Negative 3. 9 plus negative 3 is 6. 1 times 6. Negative 10 plus 6. 1 times negative 4 is negative 4. And 4 plus negative 4 is 0. Now we said there's a chance that what other number worked? 1, because at 1 it touched the graph and went back up, yes? Yeah. 1 times 1. Negative 3 plus 1. Negative 2. 1 times negative 2. Negative 2. 6 plus negative 2 is 4. 1 times 4 is 4. And negative 4 plus 4 is 0. Now there's a chance, well, so we'll add 1 back to the group. So we have 2 solutions left because we plugged 3 in, found out that they work. Have a total of 5, so we're missing 2. Now at this point, we're not too sure if the other 2 work. Negative 1 or 1 work again. But here we have what left? X squared minus 2x plus 4 minus 2x plus 4 graph. It doesn't cross the x-axis, which means our other 2 solutions are complex. They're going to be our terms with I. Now, unlike the first one we did with solving that had I, this one has a middle term, yes? Square root method is out. We're going to have to use quadratic formula or completing the square. For this one here, we'll use the quadratic formula. Now, factoring is also out because if it does not graph, does not cross the x-axis, it's not going to factor. Well, it does, but we'd have to know the factors to be able to factor it. Now for us here, A, B, C. A is the number in front of x squared, which would be 1. B is the number in front of x, which would be negative 2. And C is our number without x, which is 4. And we plug it in, so negative B, so negative 2, plus or minus the square root of B squared, so negative 2 squared, minus 4, times our A value of 1, times our C value of 4, all over 2 times A. At this point here, we do want to do some simplifying. Our negative 2 is just 2, plus or minus. 2 times 1, 2. Now at this point here, it'd be very tempting to want to type the whole thing in. Because again, we can grab the 30xs and say second square root, negative 2 squared minus 4 times 1 times 4. Domain error. Second square root, negative 2 squared minus 4 times 1 times 4. It does work because, again, we see we have I. We know we'd have I because if it doesn't cross the x-axis, it's going to have I. But that's not a decimal, is it? Well, it is a decimal. It doesn't simplify. This is part of the reason why in the 30xs, I'll plug it in here. But without the square root. So we have square root of negative 12. Well, even though the 30xs cannot take the square root of negative 12, plus or minus 2, we know that the negative is going to come out as what? I, leaving us with the square root of 12. 30xs can take the square root of 12, which is telling us that the square root of negative 12 is 2I squared to 3. So essentially, just take the negative out as I, then simplify the radical. Does that make sense? This is one of the ones that the 84 can do these imaginary roots, but it works better if the number inside there's a perfect square. 30xs can't do the imaginary roots, but it can simplify radicals. It's one over the other. Now we're completely done as long as the top two numbers are not, you're not sharing any common factors with the bottom. And it does, yes? They all have a common factor of what? 2. I'm going to show you this here because really what we can do to simplify it is we can break it up into the two fractions because really we have 2. First one, 2 divided by 2 is 1. 2I divided by 2 is just I square root of 3. So those there are other two solutions along with our negative 1, 1, and 1 that we had from the beginning. So really we do have 5. We have 1 plus I squared root of 3, and we have 1 minus I squared root of 3. Questions on this here? Questions on any of this so far? Not too bad. Other things you all probably want to do, but not the worst thing in the world. We're ready for the next theorem. We've really had this theorem. We've talked about it before, the complex conjugate theorem. And it states that if A plus BI is a solution, A minus BI is also a solution. We have to have them in pairs, complex conjugates. And this is kind of nice to know because if it says that there's only one of them, no, there has to be 2. But also if we have a degree 3 and the calculator, like it did before, gave me 2 solutions, I know that the third one cannot have I. If we only have 3 and we found 2 already, we only have 1 left. I always comes in pairs of 2. If there's 2 left, there's a chance it could be I. If there's only 1 left, there's no chance it can be I. Questions on this here? Now, there's only one theorem left that we're going to cover. We're going to cover it on Wednesday, and it's Descartes' rule of signs. Rene Descartes. And actually, the funny thing is you've actually heard of him before. At least he was also dabbled in philosophy. I think, therefore I am. Actually came from Descartes. He's also a mathematician. But I want to go back to this one here. Now this is extra. Y'all don't have to write this down. Y'all can watch this here. Now we did get the solutions, negative 1, 2, negative 1, and plus or minus 2i. 1, 0, 1, negative 2, negative 12, negative 8. Now we said 2i is a solution, yes? According to the remainder theorem, if it's a solution, if we can plug it in and it gives us a 0, it works. The remainder for this here should be what? 0. Let's see what happens if we do synthetic division with 2i. Now 2i times 1 is 2i. 0 plus 2i is, well, 2i. Now we're going to do 2i times 2i. Well, 2i times 2i is negative 4. Because I times I squared is negative 1. 1 plus negative 4 is negative 3. 2i times negative 3 is negative 6i. Negative 2 and negative 6i are not like terms. So we actually get negative 2 minus 6i. Now at this point here, again, we have to multiply by 2i. So we have 2i times negative 2 minus 6i, which is 12 minus 4i. Negative 12 plus 12 minus 4i. Well, the 4i is not like terms, but the negative 12 plus 12 gives us 0, negative 4i. And lastly, we have negative 4i times 2i, which is 8, and negative 8 plus 8 is 2. Now, doing that, well, you say, why is that helpful? Because now we've got 2i, 2 minus 6i, and negative 4i as part of our answer, yes? Well, as we just said, all of these complex terms come in pairs, yes? So if we have 2i, negative 2i has to work. Well, negative 2i times 1 is negative 2i. Well, 2i plus negative 2i is 0. Negative 2i times 0 is 0. Negative 3 plus 0 is negative 3. Negative 2i times negative 3 is positive 6i. Well, the negative 6i plus 6i is 0, leaving us with negative 2. And negative 2 times negative 2i is positive 4i, which does give us a 0. Yes. Now, again, I wanted to show you that because not so much that we're going to take too much into this, but it's very interesting that this does work, that I don't have to find each one. If it's a solution, we can use synthetic division with it. No matter how ugly the number looks, it still works, which is kind of neat. But we'll finish this up on Wednesday.